So yeah, my name is Jakob. I am a physicist by training, and I work on data analysis and software development for the experiment, which means I'm a Python and C++ programmer by necessity. So I'll start by telling you a little about, so that's me, where I work. So you saw the little DAISY logo on my introductory slide. And DAISY, you might know, is the National Particle Physics Lab in Germany. The main campus is in Hamburg. There is actually, not many people know this, but there's a branch campus here, not quite in Berlin, but just outside. So down here, so we're over here at this blue dot. DAISY's way down here at this little pin on the banks of the Dahme River. This is the astrophysics division of DAISY. So this is a Helmholtz Research Center. That means anything to you. We have about 200 scientists, postdocs, and students, and what we work on there primarily is high-energy astrophysics with gamma rays, which is the main focus, and there's a small part doing it with neutrinos. And so the experiments we hosted that we participate in there are IceCube, which is what I work on, a satellite-based gamma ray telescope called Fermi, which you may have heard of, and then a series of ground-based gamma ray telescopes. MAGIC, which is on La Palma, HESS, which is in the Namibian desert, and the Cherenkov Telescope Array, which is a future project, which will be the mother of all gamma ray telescopes, which is in development, and DAISY is one of the lead institutes on that. So that's DAISY. The experiment I work on is actually not just DAISY, it's an international collaboration spread out over the entire world, pretty much, mostly North America and Northern Europe, about 40 institutions, about 300 people total. And it's headquartered in Madison, Wisconsin. The experiment itself, though, is at the South Pole, which is very far from here. So the experiment is called, so the full name is the IceCube South Pole Neutrino Observatory. It's a lot of words. And what I'm going to try to do is unpack that for you as a motivation before I actually get into what my talk is supposed to be about, which is the data pipeline that we use to do science. All right, so we're going to start from the middle and sort of work our way out to the ends. So first, what is a neutrino in the first place? So we're going to talk about particle physics now. It'll be over soon, I promise. You may know about electrons, fairly common thing. The electron is a point-like particle. Corresponding to the electron, so a related particle is the neutrino, which is like an electron, also point-like, also has the same spin properties, but is much, much lighter. It has mass, but very, very little. It's at least 1 million times less massive than the electron, and it carries no charge, which means it participates only in the so-called weak interaction, which, creative naming, it's very weak. And just like there are 3 generations of things that are like the electron, the electron has heavier older brothers, or heavier unstable brothers, the muon and the tau. There are also corresponding neutrinos. Now, the thing that makes neutrinos interesting, apart from their fundamental weirdness, is the sorts of things that make them, and how we can use those to study the underlying processes. So one of them, the way these were actually proposed and then discovered, so the thing that gave the motivation for them is radioactive decays, a certain kind called beta decay, which changes the charge of a nucleus that proceeds by emitting a neutrino. Similarly, there's also a fusion in nuclear reactors. It's a big source of neutrinos. The sun is actually quite bright in neutrinos. If you hold up your thumbnail, which is about a square centimeter, there are 100 billion solar neutrinos streaming through it every moment. But since they interact so weakly, they almost never actually deposit energy in your thumbnail or anywhere in your body, more than a couple times in your lifetime. So those are all fairly low energy. As we go higher in energy, we can also make these in particle accelerators, like the LHC at CERN in Geneva, Switzerland. We can go up by about a factor of 1,000 there. But the really high energy ones are going to come from the natural accelerators that exist somewhere in our universe, and those are going to be even more powerful than that. We're going to go up by several orders of magnitude here. And so what we're looking for is we're looking for neutrinos from cosmic accelerators, and the reason, so what we're actually trying to learn by that, and the way we know that these cosmic accelerators exist is because of something called the cosmic rays. And so the cosmic rays are atomic nuclei, so small charged particles that are bombarding the Earth from all directions constantly. This is actually the reason why the rate of radioactivity, so of radiation, the experience on the Earth actually increases as you go up in altitude. So when you're on a plane at 30,000 feet, you're actually being irradiated much more than you are here on the ground. It's a fact that was actually discovered here in Berlin almost 100 years ago by a guy who took balloon flights up with a little radiometer and saw the count rate went up and first discovered the cosmic rays. 100 years later, we know that those come from all directions and that their energies extend quite far. There's something out there that is accelerating single protons to really macroscopic energies. There's a plot here on the left, which is an energy spectrum, and the units on the bottom are the eV, electron volts, which are things we usually use to measure chemical energies. So like the energy that an electron emits when it jumps between orbitals in an atom. And this is a log scale. It's going up quite far. We're going to numbers like 10 to the 19. And that's, once you get to numbers like 10 to the 19, that is a joule, which is a macroscopic amount of energy. That's a kilogram meter squared per second squared. That's if you take like a ball and roll it across the floor. That's the sort of energy kinetic energy you're going to have. And something is putting that kind of energy into a single proton, and that's wild. We don't know what does that, or where those are. Because those things are charged as they're making their way to us, their directions get smeared out by magnetic fields in the galaxy, between galaxies. And if you look at the sky in cosmic rays, you don't actually see like points, like stars. You see just this overall smearing. And this is the scale on this plot on the right is a part is 0.2%. So they're really, really isotropic. Now, associated with those, though, there should be production of neutrinos in the same sources that make those cosmic rays. And since neutrinos are only interact weakly, they're not charged, that means that they don't care about magnetic fields. They travel in straight lines all the time, and basically nothing can stop them. Dust and gas and radiation fields in the way that are in the way, they just don't care. They go straight through. So they're streaming through us all the time, and it would be very interesting to go detect them and see where they point to, see how many of them there are. But the very special place we go to look for them is actually the South Pole. And the reason that is, so if you see the picture of the globe, at the bottom there's Antarctica, the forgotten seventh continent. About 1,500 kilometers from the coast is the actual geographic South Pole, which has been continuous. There's been a research base there continuously manned since 1957, a year in, year out. And so these days, it's actually quite comfortable down there. We have this nice elevated station that houses 150 people. In the summertime, you fly there on this military transport plane. But the reason that this is an interesting place to be is because of what it's sitting on top of. The South Pole itself, so the station is at quite high altitude, 2,800 meters. Pressure-wise, it's even higher. Pressure is about 600 millibars. The air is quite thin. But most of that is actually just ice. So the bedrock itself is almost at sea level. And the rest of this is ice that's been deposited over hundreds of thousands of years just by basically ice crystals precipitating out of the atmosphere and then layering and layering and layering and being slowly compressed. And what you have here is a really thick ice sheet that's almost 2,800 meters thick and is about the clearest ice, is much clearer than any ice that you'd ever see up here, like the ice cubes you would take out of your freezer. There are very few bubbles in it. There's very little dust. Light can travel for hundreds of meters in this ice without stopping. And so the reason that is interesting is that you can take this ice, which is a naturally occurring medium, and you can use it. So you have a large target mass that will collect lots of neutrinos, and you can use that target mass for free if you just instrument it. And so about a little over a kilometer from the main station, which is over here, there is the IceCube experiment. And it is the outline of this is this dotted line. In the middle there is the IceCube lab, which is our data center. And so what was done is to melt holes in the ice that go 1.5 kilometers or 2.5 kilometers down, and to lower sensors into them, light sensors, basically pixels of a super fast camera. And what that gives you is the detector we call IceCube. And so this is a sketch of it. So on the surface here, there is the IceCube lab, and then there's 1.5 kilometers of hole, and then the bottom kilometer is instrumented with these things called digital optical modules, which is a pressure sphere with a photomultiplier tube in it. And what that ends up being is just a single pixel, very fast camera. It can see single photons, and it can resolve the time at which they arrive to within a couple of nanoseconds. And the reason that's interesting is because when neutrinos interact, they deposit energy. That energy is going to go into charged particles. And if those charged particles are traveling faster than the local speed of light, that charge is shoving electrons in the medium out of the way. And they can't get out of the way fast enough, and so you end up with basically a sonic boom in light. It's called the Cherenkov effect. And this might, if you've ever seen a photo of a reactor cooling pool, this eerie blue light that comes out, that's what you're seeing, is this Cherenkov light. And so there's this bow shock in front. And you can use that, we can pick up those photons and use that to tell where the neutrino came from and how much energy it had, and those sorts of things. All right, so that's the experiment. And now I'm going to talk a little bit about how we handle data in this experiment and use that to find neutrinos. So this is what our data pipeline looks like. One of the things that's different from every other data pipeline that you will probably ever see is that there's this dividing line here, this dotted line here, which divides us into parts that happen at the South Pole, where communication is very limited, power is very expensive, and things that happen offline in data centers in the north that we can power with cheap electricity and that we can actually go in and fix. So in this pipeline, first we have to acquire the data and then calculate features on that data and select it down. So most of the data that we collect is actually background. It's uninteresting events. So we need to cook that down to an event, to a sample that's mostly made of neutrino events to do our data analysis. And at the same time, which is also a little different from applications that we hear about here, the questions we want to answer are questions about the underlying properties of the neutrinos that we're seeing. And since we don't actually have a high energy neutrino source, we don't have one of these cosmic accelerators that we can just put anywhere in the universe and flip it on and off to tell us what it should look like in our data. So we actually have to simulate our detector, which is very computationally expensive. So we actually have to, in a computer, model the process of how a neutrino interacts and how it dumps energy into the ice, and how that energy gets turned into photons that we can see. And then we take those events and we pass those simulated events to the same pipeline, so then you have a set of real data and simulated data that you can then put through your data analysis and in the end get out science. So one of the main challenges here is, as I said, actually getting the data out of the South Pole, getting it processed to a form and doing an initial selection where that will actually fit over our satellite link. Then also generating the simulated data. It's also computationally expensive and requires some coordination. And I mentioned before that this data is then fed to an international collaboration that has a lot of people in it, not all of whom have exactly the same interest. This isn't all going into one monolithic analysis that only has one result. There are probably about 15 or 20 distinct science topics, and the people working on those are not necessarily experts in data processing, or they should be experts in analysis by the time they finish, but we shouldn't expect them to be experts in the processing and feature extraction before they get there. And so we need to allow them to configure this processing pipeline and to extend it for their own work with a minimum of effort and without making it hard for them to blow their own legs off. And then the end is part of that, actually distributing the data to the downstream analyzers. All right, so I've talked a lot about our data. What is our data? So this is what our data looks like. This is a neutrino event. And so what you see here, this is a 3D rendering. Actually, a lot of the background for this is actually written in Python. But what you see here, these vertical lines are so-called strings of IceCubes. This is a cable that hosts 60 of these single pixel detectors. And between these is 125 meters. So this is actually quite big, what you're looking at here. And in this event, coming from the left, which you don't see, is a neutrino. And nothing's happening around it. It interacts somewhere here in the middle and then creates a particle called a muon, which is, as I said before, the heavier brother of the electron. Because it's so heavy, it's very penetrating. It doesn't stop very quickly. It gives you a long track to the detector. And what our data look like, each one of these dots here represents one of these DOMs, one of these pixels. The color of that dot denotes the time at which it was detected, which is on the color scale here on the bottom. So this whole thing is we're looking at 6 microseconds in time, and the size is the number of photons that it saw. And so from this data, you can tell that since there was nothing over here on the left side here, that was a neutrino, and that from the pattern of hits here as it goes out, you can reconstruct the direction, and from the amount of light collected, you can infer the energy. Now that's what a nice event looks like. That's the end product. What we're getting it from is data that looks like this. It's kind of messy. So this is a longer view of the detector. This is just what if you just read the detector out for 10 milliseconds, this is what it would look like. It just lit up like a Christmas tree. For every neutrino we see, there are actually 1 million background events, which are penetrating muons created in cosmic ray air showers. So these muons actually are energetic enough to make it down from the surface and enter our detector, and that's not really what we want. Those aren't the most interesting thing. And even once you've cut out that first factor of 1 million, you're still not there. Most of the neutrinos you see then are fairly low energy, also not terribly interesting. And the ones you're really the most interesting ones are actually quite rare. There are only about 10 of those a year. And so if you want to make that down selection from 100 billion events a year to 10, then we need some framework for calculating features on the data in an efficient way. And so that's what I'm going to talk about next, which is the feature calculation and the data selection. So try to make this a little more data sciencey, calling it feature calculation, and we call it usually just reconstruction. All right, so we have a framework for this that is maintained by a core group of about 5 to 10 volunteers, and we call it ice tray because you put ice cubes in an ice tray. Haha. The core of this is in C++. There's about 20,000 lines in the core. If you add the data storage classes and a lot of the algorithms that are then supplied as modules, then that goes up to 80 to 100,000, depending on which distribution you're using. Now the core is in C++. Way back when, so before 2008, we used to require users to write C++ to use this. That was not great. One of the best things that was done at that time was to take the Boost Python library and use that to expose, to write Python bindings for almost the entire suite. So you don't even have to know that this is written in C++ to use it, which is quite nice. That's made things very easy, and this uses Boost quite heavily. Since we do now with C++ 11.14, that's less necessary, since basically what happened with C++ 11 is some new language keywords were added, and then they imported all of Boost into the standard library. So things have gotten much better, as was mentioned this morning. So there are 2 main components to this framework. One is the data container, which we call an i3 frame, different from Panda's data frame, predates it. So this is a container for an event data, for all the data relating to one event. And so that is the object that's passed back and forth in this framework. And the things that do the passing back and forth we call i3 modules, different from Python modules, a lot of name overloading here. What that is a single unit, basically similar to, this is basically like processes and pipes. In Unix, this manipulates it takes i3 frames, does something to them, and passes them to its output. And all of our data storage is done in files. Because of the way we're distributed across the globe, it's not really feasible to stick all this in databases and still have it be available at the level that it needs to be for analyzers to work efficiently across continents and in different time zones. All right, so the i3 frame is basically just a giant dictionary of C++ objects that are immutable. So you can keep a pointer to this and be confident that no one's going to change it under your feet. And they're all related to a single event. And so, as I mentioned before, they're Python bindings. And so to read one of these, you pop it out of the file, and then you get, this is an example event. There are objects that are related to, say, the geometry or the pulses, which are the photon records. And then you can take those and calculate derived quantities on them. our file format is just you take this frame and then you serialize it and you dump it to disk, so it's just a stream. It can contain one or more frames. And this is all backed with the Boost serialization library. And that gives us all the load and save operations. In particular, in contrast to something like Pickle, you get object versioning. So you're allowed to change, you're allowed to update your classes and then be able to read old versions and upgrade them at a later time. So you get backwards compatibility, which is kind of nice. But not forwards compatibility because you don't know what you're going to do in the future. So so that's the data container. The interface for manipulating these are i3 modules. This is just this is a processing stage that does ideally one thing and does it well. And to configure a processing chain, you do this in Python and you just string these things together. They're like building blocks. They don't need to know about each other's implementation details, and all you have to do is configure them with appropriate keywords. And the things what these are allowed to do is relatively restricted. They can add things to the frame, they can remove them, or they can just decide to drop the frame entirely, and that's how you do filtering. You just drop them out of the processing chain. And it's fairly compact. You make this tray object, and then you add things to it. A typical script here just has a reader at the beginning and then a writer to write it out, and something in the middle. And then that's the configuration, and the actual inner loop is in that execute method. We also, since we are really into exposing things in Python, we allow new modules to be written in Python. So this is actually just this iceTray.i3 conditional module here is an instance of Boost Python class that allows you to extend that. When you call into this from the C++ side, it actually drops into the Python interpreter, executes the code, and then returns the result appropriately cast to the expected return type. And so you can write something really simple where you add parameters and then you get them and then you do things to each frame. And one thing this has allowed us to do, this is a pretty brain dead example, but it's allowed us to really prototype rapidly in Python. And sometimes that carries a performance penalty because this is a tight loop and looping is expensive in a dynamic language like Python. Then you can rewrite it in C++ if you need to. And especially with physicist code, physicists tend to write code that just works and not really worry about whether it's nice or not. And this allows you to, it's sort of an enforced prototyping stage. You have to rewrite it if you want it to be fast at some point. And it enforces a little bit of discipline, which is nice. So so as I said, that first stage of filtering happens at the South Pole. The detector is read out 3,000 times a second. The average size of one of these event data payloads is about 4 kilobytes. And so that works out to generating about 1 terabyte a day. The South Pole is only, there's no fiber running to the pole. There's only a satellite link, and since it's at the South Pole, geostationary orbits work really terribly at the South Pole. And so the satellites we use for communication aren't visible all the day. They're up on average about 6 hours. And so we have a relatively small bandwidth allocation, about 100 gigabytes a day. And so we filter out 90% of our data before we even send it north. And that fills our bandwidth allocation. That all goes to a data warehouse, which is a large Lustre cluster in Madison, Wisconsin. We now have 4 petabytes and counting as we just accumulate data. Not all that is actual experiment data, though. There is also simulation. So I'm not going to say much about it, except that it's very computationally expensive, and just mention how we do grid computing as opposed to cluster computing. So in the academic world, we don't tend to rent space from Google or Amazon, since our accounting departments really don't like unpredictable pricing. But we have computing farms that we own, and also there are collaborations with institutions in Europe and the US that allow opportunistic use of each other's clusters. And so those are scheduled with a system called HC Condor, and what that basically gives you is the ability to run a process on some sort of Linux flavor. You'll know what it is when you get there, but it's usually a Red Hat variant, and also a system for provisioning your experiment software on a read-only file system that has lots of caching layers and is fairly robust. All right, so once we've done the processing, then it's time to move on to the actual analysis. So this I3 frame that I mentioned is very flexible. That's the idea. We want basically the schema to be able to change from event to event. But once you're actually ready for your analysis, that's not the most efficient thing. In particular, since this is just a giant map of irregular data, reading one field out of each event can be very inefficient. And so what we'd rather have for that are tabular formats. And so we also have a framework, was one of the things that I contributed, for turning this irregular data, for hammering it into a tabular form that you can read into your favorite analysis tool as an array and do things with. And so for each type, there's a specific converter that does the coercion and maybe some reduction and summarizing and puts that in an abstract data structure. There's just this general table row. And then we have format-specific backends. Since, of course, we don't all use the same tools, there is people who come more from the accelerator community, more from the real high-energy physics, use this toolkit called Root, which is a thing that was provided by CERN and lives in its own little world and is orthogonal to the rest of computing. And there's, I guess, sort of a generational thing. A lot of people like Python. And so we write this out to HDF5 tables. And those can then go into, be read in with Pi tables very nicely, or with pandas through Pi tables, or H5Pi, and a lot of different things. All right, so the actual analysis is usually is much less exciting than the data processing, it turns out. So the procedure for most analyses is actually kind of bland. So usually it's done with binned data. And there's a lot more than happens in other fields you fill the data into a histogram, and then the histogram basically is the data. That's what you do your analysis on. And the reason we do that is because it's really easy to understand when you're writing this up in a paper how you got to the statistics. You can just predict. You can predict the mean in each bin in a fairly straightforward way, and then calculate statistics on that in a way that's easy to explain, and that makes it easy to get papers accepted in the community. The disadvantage is that you have to actually choose the binning, and especially if you have small amounts of data, then that's a choice that can bias it. And the way we usually get around that is or isolate ourselves from that bias, is to develop these analyses without actually looking at the experimental data, and actually do it blind, and only know what the data looks like once we've fixed all the parameters like the binning choice. A little advertisement, since histograms are very important, or much more important to us than they are to the rest of the community, we have developed some custom tools. One of this is a little package called Dashi that was developed by a grad student in Zeuthen and has been adopted by a lot of people in IceCube. And so this is basically, instead of having just this histogram function like in NumPy, you actually have an object that internally does its actual binning with the histogram function, but also has a lot of handy tools built in. Like, it can tell you what its mean is, and you can manipulate them, you can add them together, you can slice them, you can project them, and you can also store them later. Sometimes if you have hundreds of millions of points to fill into a histogram, you don't have to refill that every time. And so you can store them in HDF5 files as shown here, and it's on GitHub. All right, so as an example, there was a paper that was published in 2013, which was the thing that IceCube is so far best known for, which is the actual discovery, the first evidence that these high-energy astrophysical neutrinos that I've been talking about actually exist. Before that, they were just hypothetical. So this actually used a very simple event selection. There was no machine learning involved. Unfortunately, other ones do. But in this case, you can actually get away without it. So just two features. You set a threshold number of photons, which is a large number, and that takes that 100 billion events down to only 1 million. And then you demand that the hit pattern actually starts inside the detector, which is a thing that only neutrinos can do. And once you do that, you end up with only 28 events left. And then the question that was asked for this analysis is a really simple one, which is, so there are these high energy events. They look a lot like they're astrophysical, but they could just be a fluctuation of the data, and the fluctuation of the background. And the thing to exclude is that they are just a fluctuation. So the question you ask is, so we have these 28 events. They have fairly high energies. What is the chance that they're a fluctuation? And quite literally, the thing that is done is to take these data. So here are all the data points. plotted in energy and angle, and to fill those into two-dimensional histogram, and then compare the counts in the bins of that histogram to the predicted mean from simulation using a Poisson likelihood, and then calculate the test statistic and ask how often that should arise by chance. And the answer, luckily, is that that happens less than 1 in every 2 million trials, and so that is what we call 5 sigma. It's a discovery, and then we went and published that in this paper here. Okay, so I've told you about now, I think I'm almost out of time, but about IceCube, which is a cubic kilometer detector at the South Pole that uses neutrinos to look into the universe, and that we are very happy users of Python in our processing and our data analysis. And with that, I will take questions.
Thank you, Jakob. Questions?
Who's your ISP in the South Pole?
So our ISP is the Antarctic Support Contract. It's actually Lockheed Martin. It's yeah. I'm not going to say anything about them because this is probably being recorded. So, yeah, it's the security is very important to them, and yeah. So it's the local infrastructure is managed by Lockheed, and the satellites we use belong to NASA.
Thanks for the talk. Really interesting to see fellow astrophysicists here. So what was the background fluctuations you were talking about? So the noise from which you're trying to disentangle your signal?
So the noise is just so in addition to these high energy astrophysical neutrinos, there are also neutrinos that are made in air showers in the atmosphere. And it could be that you just happen to have ended up in a year or ended up with a series of overfluctuations where you had ones that are very high energy just by chance. It can happen, and that's a thing you need to exclude. And they're on the face of them not distinguishable from astrophysical neutrinos. We just do it, we can only make the distinction by energy and angle.
I was wondering what the reason was to do this on South Pole. Is it only because there's a lot of ice, or is it also the environment or the local atmosphere that play a role?
So the main reason to do it, so you need a lot of material. So you need a lot of water or ice. Ice has its own advantages. It's mechanically stable, and once it's frozen, everything becomes stable, and you don't have to worry about your detector units imploding under the pressure once it's become stable. But the reason to do it at the South Pole specifically is because it's a place that already has communications and power and is sitting on 2.5 kilometers of ice. There's actually a consideration to do it in Greenland. Could have also been done, but would have been much more expensive. And the station's already there. It's already being, the extra power budget to run IceCube is not that much, and so it's less expensive than it would otherwise be.
No more question? Come on, one question. No? Maybe I'll ask a question to close. Oh, no, here. All right.
Hello. I wonder if in the experiment, when you collect the data, I guess that there is a certain uncertainty within the measuring of the data you are doing the analysis. That can bring some noise in the data itself, the method where you are collecting that data. So it's how you are measuring the the actual methodology of collecting the information?
So yeah, so the experiment itself does introduce biases. There are trigger thresholds, so the detector is not read out unless there are a certain number of photons are collected in a time period, and so that does introduce an energy threshold. But that's important at very low energies. At the high energies, the biases are fairly small, but the data itself is also noisy because the data itself are counts of photons, and they have statistical fluctuations in them too. And so, for example, we can't reconstruct energies exactly. We can only give confidence intervals that have basically 1 over square root n noise in them.
So I have a second question, and it's about open science. Do you release the data and the packages so other teams can double check or?
So my answer is almost. So we are required. So this is funded by the U.S. National Science Foundation. One of the conditions of that funding is that we do release the data. We do not release the raw data, nor do we actually release these tools. And most of that, as you may know, the reason that things are closed source is not usually because they're so great. It's because so we don't really have the funding for a full-time data release manager who would actually go out there and be available full-time to support people doing analyses on this. Other experiments are different, like this Fermi experiment I mentioned before. NASA actually provides a data support team who are there only to maintain the tools and to provide user support on the outside. So what we typically do is we provide these, so we don't actually provide the raw data, but we provide these histograms that are used for analysis. And so to the best of our ability, we provide tools to reproduce exactly the analysis that was done, but it's not necessarily extendable to others. But so our goal is to release data. We're not always able to do so in a way that is easily usable, unfortunately.
Okay, if there are no more questions, maybe we can break for lunchtime, I think. So thanks again, Jakob.
Yeah, one last shameless plug. So if you are interested in the science and you are local, I would encourage you. In a few weeks, there is the Berlin-wide science open house called the Lange Nacht der Wissenschaften, and especially in Adlershof at the HU Science Campus, there are a lot of events like this. There'll be a lot of talks, a lot of hands-on activities for the kids. If you have kids, bring them; they'll love it. And so, yeah, check this out if you'd like. Lange Nacht der Wissenschaften.